been discussed already, so I'll add to that. Okay. The slide is not advancing. Let me try. Okay, there we go. I think I want to go beyond San Francisco because I look at simulations in Los Angeles and other places as well. And I think it's important to recognize the past. The seismic response and the damage and the 10,000 people who were killed by an earthquake that was over 300 kilometers away in 1985 in Mexico City is very important. And we should understand the importance of how that soft clay, that soft soil amplified the ground shaking. And it essentially took a fairly benign ground motion on firm soil and amplified it to the point where it was highly destructive to buildings that had period ranges around the range of that ground motion, which is because of that particular depth of clay, and its stiffness was around 2 seconds. The late Professor Harry Seed, who worked on this 85 Mexico City earthquake, used the equivalent linear shake analysis, which is really the most basic fundamental aspect of doing site response and capturing the nonlinear behavior. It does so in an equivalent linear version or way, but it captures the strain-dependent shear modulus and damping. And with that 1D, relatively straightforward program, he was able to capture the dynamic response that was recorded that was so damaging in Mexico City. Fast forward to 2017, there was another closer earthquake that had energy coming in from the rock and the firm soil at a different period range. And now we had a different part of the lake bed. The Mexican engineers understood the importance of site period, and so they have different zones. And in fact, the soft clay zones, zone 3, is divided into zone 3A, 3B, and 3C, primarily because of the depth or the thickness of the soft clay in those areas. The damage in terms of collapsed buildings was largely in the zone 3A. You can see the concentration here. And that's different than in 1985. In 1985, because of the energy coming in, having a period more around 2 seconds, it was the deeper deposits of clay that really responded to that ground shaking. And you see the significant damage of the blue buildings in that location. And so if we're going to be able to estimate damage from different earthquake scenarios, we have to be able to capture this very important effect. You can see that in the recorded spectrum of a ground motion in the area near the damaged buildings, amplifying ground shaking that was on the order of 0.8 seconds to 2 seconds, which was very damaging to the buildings in that area that were shaken by that earthquake. Now we go to 89, and at that time, the code did not fully capture the important aspects of soft clay. That's something that the late Professor Harry Seed had been working on. But when we saw that earthquake and the damage at some distance away from the rupture zone, we saw that there were soft story collapses. And again, the structural engineers will point to the fact that there are soft stories, but there were soft story buildings in Presidio that were not damaged. And so it's vulnerable structures, but then it also is the soil conditions changing the ground motion to the point where they're incredibly damaging to the structure sited there. And in fact, the liquefaction of that led to the fire that almost became a traumatic experience from that earthquake was in the Marina District, where you have these soft clays with the liquefiable soils on top. When we did the reconnaissance for the 1989 Loma Prieta earthquake, we saw that there was landslides and damage in the area above the rupture zone, but at some distance away, 60 to 80 kilometers, most of it was huddled along the edges of the bay where you have these soft clays that amplified the shaking. In fact, right after the earthquake, this was a simple little exercise we went through, taking the ground motions that have been recorded, just looking at the fall off of PGA with distance to the source, with different site conditions. We recognized very quickly that these softer soils at a distance of about 60 to 80 kilometers were significantly higher intensities in terms of PGA than the stiffer soils and the rock. And so this map is appropriate in terms of having the color red represent the soft soils or the bay mud sites. We talked about the Marina District. There was also increased damage in a relative sense because of the amplified shaking along the margins of the bay. But probably the most famous pair of rock and soft soil site recordings are Treasure Island and Yerbuban Island. Obviously the ground motion coming in and the source and path effects are relatively similar, these close records, but the characteristics of the rock motion, which is Yerbuban versus the Treasure Island motion, are significantly different in terms of amplitude, frequency content, duration. And as design engineers, we focus on 5% damp spectral acceleration. You can see the significant amplification, not just at the PGA, but at longer periods because of this soft soil. Something closer to home, I was at UC Berkeley at the time, and one of the ways that I would travel back to my apartment in downtown Oakland was to go along Highway 80 and go through the Cypress structure. The Cypress structure collapsed, and we were lucky that there was a World Series between the San Francisco Giants and the Oakland A's, where the second game started at 5 p.m. on 17 October 1989. Otherwise, on a normal Tuesday, 5 p.m., this was wall-to-wall traffic. Still, 42 people were killed, and if we want to be able to understand why this system failed, structural engineers will point to the poor detailing, and Jack Maley and a number of structural engineers have talked about that. But I want to emphasize that along with the collapse section, there was the no collapse section. And Evan earlier today talked about that. If we look at the soil conditions, the older maps clearly show that. The people, when they first started to settle in Oakland, they went to the firm soils, the stiff soils, and developed the city. And only later did the city expand and start to fill over these soft clays. And it was that soft clay that led to the greater damage. The dotted part here is the part that collapsed, but very importantly, the part over the stiff soil did not collapse. And so it's the same vulnerable structure, but we have collapse and death to the north in the soft clay, and we have at least a non-collapse issue when we get to the same structure on top of the stiffer soils. And the aftershocks show that, but you also see it for the main shot. And in fact, this is a ground motion where we're just doing a 1D site response with a fully nonlinear model. And the only difference between these two profiles is we have the stiff soil on top of rock, which represents the southern part of the Cypress structure. And then we have the soft clay, the Young Bay mud on top of stiff soil over top of rock. And you can see that the stiff soil amplifies the outcropping rock motion, which is deconvolved, so it's a within rock motion is what I'm showing you. But it also, you can see how that soft soil on top really amplifies things and leads to additional damage, or has the potential to lead to greater damage. I remember when that earthquake occurred, the Southern California engineers, there's a structural section in the south and there's a northern section, saying, well, that's a soft soil. We don't have Mexico City clay in Los Angeles. We don't have Young Bay mud, San Francisco Young Bay mud in Southern California. That shouldn't really necessarily be something that we design for across the entire state of California. Well, it was interesting to look at the damaged buildings from the 1994 Northridge earthquake. And there's a lot of focus on near fault effects. It's a very important earthquake from that. There's a lot of damage in the area above the fault rupture or to the north of the fault rupture because of those effects. But it was striking how there were pockets or localized damage. We see this for every earthquake. We see it for the 1999 Cojali earthquake. We see it for other earthquakes where softer soils from these ground shaking tend at these lower intensities of the rock, amplify the shaking and create these pockets of damage. There was in Sherman Oaks, Universal City, through Los Angeles area in Culver City, and Santa Monica. I put this on a map of potentially liquefiable soils. And I'm not arguing that liquefaction was the issue here, but where you have these softer soils, you can have buildup of pore pressure that can create a softer response. And a lot of these softer liquefiable soils are on the old riverbeds that have some of these softer soils. So this is a case where we're saying that the soil conditions appear to have contributed to the pockets of the localized damage. And in fact, the Santa Monica Freeway is an excellent example. It is a freeway that has multiple overpasses, yet only one of them failed. One is too many, but only one of them failed. So similar structural details along this highway, and we had a collapsed section. And if you look at the word, this was in La Cienega, which translates to the swamp. And it's a recurring theme that these localized soil conditions, these softer soils, create these issues. But let's step back to 1967 Caracas. The late Professor Harry Seed looked at this as well with his graduate student Alonso, and they said what people care about is the percentage of buildings that are damaged. And so this structural damage intensity is just within a block, the percentage, the number of buildings that could be damaged, and in the number of buildings that were damaged divided by that total number of buildings that could be damaged. And he's mapping this as the number of stories. So the shorter the building, the shorter the period, a natural period, and the depth of the soil. And I've just put down here using the familiar formula 4H over VS, 1 second, 2 second, 3 second. You can see as you go to deeper stiff soils, you go to longer period response amplification, which then coincides with the longer period, natural period of the structure and the more significant damage. So the shorter buildings, short periods are damaged over the shallow soil sites at a higher rate, and the taller buildings are damaged at a much higher rate over the deeper soils. And so this simple calculation where I just took a generic magnitude 8 ground motion scaled to 0.3 G, deconvolved it down and propagated it up through different profiles where everything essentially is the same, we just lengthened the profile. And you can see that as you go to deeper soils, you go to a response more in the longer period range. And so we need to capture that. Soft soils are like putting a filter on top of that. And the same type of analysis was done. I just put about 20 meters of soft clay on top of that same profile with the different depths of bedrock. And you can see that then it really takes that energy near that period of the soft soil column and really amplifies that. So that's another thing that we need to consider. The other aspect is nonlinearity. So the Loma Prieta earthquake and some of these earthquakes, the ground shaking for outcropping rock was 0.1 G, 0.2 G. We're in that range where we're getting the peak run acceleration to get amplified. Very importantly, as you get to more intense ground motions, then because of nonlinearity, which is important to capture in any kind of simulation, you're going to expect that actually you'll get to a crossover point and get de-amplification. For a stiff soil site, that might be 0.6 G. For a soft soil site, that might be 0.4 G. For stronger sites, it might cross over at 0.8 G. But if you're going to capture things across the entire range, it's important. And we focus a lot of times on the big event, but I think a number of speakers have already talked about the smaller events are important. A magnitude 6.5, a magnitude 6.2, a magnitude 6.8 is going to occur more frequently, and the amplification that you get at some distance away is going to be the difference between whether that threshold of damage is reached for vulnerable structures or it's not reached. Now, we've recognized that, and for example, the NGA West ground motion models, many of them incorporate the work by Sayin and Stewart that brings in nonlinearity. So if they have a site factor, it doesn't just have the linear amplification, but it has a nonlinear. And that works across, in a global sense, it works across the entire period range. It's largely a function of VS30 and PGA of the rock. Those are the two key inputs. And the code follows that as well. Because site class E, the soft soils, and site class F, which includes very soft soils or thicker deposits of soft soils or organic soft soils, we thought it was important to specifically look at trying to not, in a more specific way, capture the unique personality, the characteristics of these softer sites. And so we have the amplification as a function of different periods. Of course, it's a function of the intensity of the rock, the nonlinearity, but to be a little bit more sophisticated and more complicated, but trying to capture things better, we have the thickness of the soft clay, we have the shear wave velocity of the soft clay, the strain that develops because it's a nonlinear problem, as well as the strength cutoff. With that model, we then do fully nonlinear effective stress analysis. This is for a suite of ground motions that were scaled by a factor of 2 and 4, and they were scaled down by a factor of 0.5 and 25% and 12% to look at not just ground motions at the baseline, which was a magnitude 7.8 at 30 kilometers shallow California earthquake, but to look at nonlinearity. We can see that this is not a round spectrum. We'd expect a site to have its personality, and we can see that as we change the intensity of the ground motion, we get the shift of the period, and that the simplified method, which brings in more information, is able to capture this. A key aspect of this is being able to capture how the nonlinear response of soil evolves during ground shaking. And a key element is making sure that your model includes nonlinearity already up to and including failure. A lot of our curves in the laboratory don't go all the way out to failure. So it's very important, and you had all talked about this in 2013, is to make modifications to your shear modulus curve to be able to capture the actual strength, which is shown in red, as opposed to the inferred strength from the standard laboratory curves. And so geotechnical engineers understand if you're going to do a fully nonlinear analysis, you're going to go to large strains, it's critical that you adjust the curve, the modulus reduction curve and damping curves to be able to capture response at a large strain and hence capture things like strength. From my experience doing this work and also peer reviewing work, I think key things that we feel you have to capture in the empirical evidence supports and analytical study support for a soft clay response is the details of the soil stratigraphy are very important. Whether you have fill, soft clay, stiff soil, or you have a gradation. We often have simple shear wave velocities as being constant with depth. The effective stress principle says that's not true. For a similar aged material, we expect things to increase. And if we do detailed measurements, we see that increase with depth, and that has an important impact. The dynamic peak strength has to be adjusted for rate effects, which will increase it, cyclic degradation, which will decrease it. If we go to large strains, we can actually go beyond peak and go down to residual. Examining things like the shear strain profile and looking at the concentrations, and are they reasonable? Always comparing whatever you calculate with empirical and simplified methods, which are based on empirical data, and then doing a sensitivity analysis because there's some variability and uncertainty in the shear strain. My last point before getting to conclusions is VS30. And I think we've talked about VS30 and its limitations many times, but this is 3 soft soil sites in San Francisco that have about the same VS30, but they have different natural periods. They range from 0.44 seconds to 1.13 seconds. I think most structural engineers would agree if you have a building that has a period of 0.44 or 1.1 seconds, they should respond differently. Well, these sites are going to respond differently because of their natural period. So in summary, the key aspects of site effects that I've tried to point to is, yes, the stiffness of the earth materials matter. And it's not just the soft soils and the very stiff soils, obviously everywhere from hard rock to soft rock. Capturing the site stratigraphy, and then very importantly, the depth of bedrock, which we typically take as the depth to the significant impedance ratio where the material below it is rock-like. And then the simulations have to capture nonlinearity. The material stiffness and damping will vary with the induced shear strain. That means they will vary with the level of shaking. Thank you very much.